In this lecture series, you'll be introduced to IR spectroscopy, or infrared spectroscopy. And this is a technique that we use to help us characterize molecules, or to figure out what we made when we run a reaction. In all spectroscopies, we're basically irradiating our sample, our organic molecule, with light or energy, and watching its response. The various kinds of spectroscopies differ in the wavelength of light, or the energy of the light that we're using. In IR spectroscopy, we're irradiating our sample with light in the infrared region, 10 to the minus 6 to 10 to the minus 4 meters. This is nanometers or millimeters in wavelength. This graphic on the top of the slide is what a typical IR spectrum will look like. The y-axis is transmittance, or how much light is transmitted through the sample versus how much is absorbed by the sample. The x-axis is frequency. Each peak or absorption in the spectrum corresponds to a specific vibration or rotation of the molecule. And that means that the different bands or absorptions in the IR spectrum can tell us about the structure of the organic molecule, and in particular, what kinds of functional groups it has. And you'll see charts like the one on the bottom here, which tell you what bands or absorptions in a certain region of the spectrum will correspond to. So in blue here, bands in this region from 2500 to 4000 wave numbers will correspond to OH or NH or CH stretches. In red, bands in this region will typically correspond to triple bonds, carbon-carbon triple bonds or carbon-nitrogen triple bonds. And so each region of the spectrum can point us toward specific functional groups. And in this video, we'll see where these frequencies come from, what features of the molecule influence the frequency, so that you aren't just memorizing all of these values, but you understand why some frequencies are higher than others, and you can then predict the stretching frequencies for different compounds. First, all molecules are in constant motion. The bonds are stretching and bending and rotating at room temperature. And these stretching and bending modes are what we see in the IR spectrum. We'll focus our discussions on the stretching vibrations because these are typically the most characteristic of individual functional groups within a molecule. When a bond stretches, we can think of it as a spring connecting the two atoms or the two portions of the molecule on either side of the bond. The stretching or compression of a bond, as in a stretching vibration, can be thought of as a harmonic oscillator, meaning we can apply Hooke's law so that the frequency of vibration, or nu, depends on two things. First, it depends on the stiffness of the spring, the force constant K. And second, it depends on the masses on either side of the spring, M1 and M2. And these two features relate directly to our molecular structure or our functional groups. Looking at the force constant first, a larger force constant will give a higher frequency, K. The force constant is directly proportional to nu, the frequency, and the force constant is related to the bond strength. So that means a stronger bond will have a higher frequency. If we were to compare a carbon-carbon triple bond with a carbon-carbon double bond and a carbon-carbon single bond, we'd expect the triple bond to have the highest frequency because it has the strongest bond or the largest force constant. And that's what we see. A triple bond shows up around 2150 wave numbers, a double bond around 1650 wave numbers, and a single bond around 1200 wave numbers. And just to correlate that with the charts that you'll often see, that's visible here. The carbon-carbon triple bond is at a higher frequency than the double bond, which is at a higher frequency than the single bond. In the case of a triple bond versus a double bond versus a single bond, we know which one is stronger, which has the larger force constant. But some other cases are more subtle. There are a few factors that we can look at that will influence that force constant, that bond strength. And the first is hybridization. Remember, we've seen that bonds with more S character are stronger bonds. That means that bonds with more S character will have a larger force constant and will have a higher frequency absorption. The second factor is resonance. And we've seen resonance in terms of stabilizing negative charges, but we can also think about the influence that resonance has on bond strengths. So for the two structures shown at the bottom of the slide, if we were to compare the bond strength of the two carbonyls, the two carbon-oxygen double bonds, the structure on the right has resonance, and that resonance structure has single bond character. So in this case, the resonance donation reduces the double bond character of the compound on the right, which results in a lower force constant and a lower frequency. So the compound with the alkene adjacent to the carbonyl will have a lower carbonyl stretching frequency than the compound without the alkene. The third factor that we'll consider is the influence of nearby electronegative atoms. Remember that inductive effects pull electron density through sigma bonds, and in this way inductive effects can influence the bond strength. For example, if we compare this ketone with the acid chloride, again thinking about the carbon-oxygen double bond stretching frequencies, the chlorine is inductively withdrawing, it's electronegative, and it pulls electron density toward itself. And that inductive effect strengthens the CO double bond by reducing the contribution from the single bond resonance form. This means that the acid chloride will have a stronger CO double bond, a larger force constant, and that carbonyl will have a higher stretching frequency than the ketone. We've looked at the key factors that influence the force constant, and those in turn affect the vibrational frequency. When thinking about the frequency, though, we need to also consider the masses on either side of the spring or the bond. The vibrational frequency, nu, is inversely correlated with the masses, and so a greater mass will lead to a lower frequency. A lighter mass will stretch and compress faster with a higher frequency. And here we can think about carbon-halogen bonds. We can compare chlorine to bromine to iodine. And we'd expect that as we move from chlorine to bromine to iodine, as the masses get larger, the vibrational frequency would get smaller. And again, that is what we see. A carbon-chlorine bond will have a frequency of about 750 wave numbers, a carbon-bromine bond about 600 wave numbers, and a carbon-iodine bond about 500 wave numbers. Let's pause here for a concept check. For each of the following bonds, which would you expect to have a higher vibrational frequency? To answer this question, we need to remember Hooke's law. So I'll put it down here in the corner for us to refer to. In the first case, we're comparing a carbon-carbon to a carbon-hydrogen single bond. The difference is the carbon atom versus the hydrogen atom, which have very different masses. Hydrogen has a smaller mass, which is inversely proportional to frequency. So the carbon-hydrogen bond will have the higher vibrational frequency. In the second case, we're comparing a carbon-oxygen single and double bond. Here the double bond is stronger, it has a larger force constant, and so it should also have a higher vibrational frequency. Finally, in the last case, we're comparing the carbon-nitrogen single bond stretches in these two different molecules. The bond is the same, so we need to look elsewhere in the molecule for the difference. And the big difference here is resonance. In the structure on the right, I can draw resonance structures using the lone pair of electrons on the nitrogen, and I can resonate them through the aromatic ring. In these resonance structures, the carbon-nitrogen bond has double bond character, and so we would predict the structure on the right to have the stronger carbon-nitrogen bond due to that partial double bond character, and so it will have the higher vibrational frequency. One more piece to discuss before we end this lecture video. So far we've been focusing on the factors that determine the frequency of vibration, the x-axis of the IR spectrum. Now we'll look briefly at the factors that influence the intensity of a vibration, the y-axis of the spectrum. And notice here that a more intense vibration is one that comes closer to the bottom of the spectrum. Intensity increases down the y-axis. And in IR spectroscopy, that intensity is a function of the dipole moment of the molecule. And more specifically, a molecular vibration will be IR active. It will show up in the IR and be an intense band in the spectrum if the dipole moment changes during the vibration. So what does that mean? Well, a carbonyl, carbon-oxygen double bond stretch, actually stretches along the dipole moment of the molecule. And so as it stretches, the dipole is affected. So a carbon-oxygen double bond stretch will be a very strong vibration in the IR spectrum. If we compare that to a carbon-carbon double bond, here there's no dipole moment, so when that bond stretches, there's no change in the dipole moment, and that will be a very weak vibration in the IR spectrum. Other strong or intense vibrations are things like carbon-oxygen single bonds. Again, that stretching mode is aligned with the dipole of the molecule. OH and NH stretches are also strong vibrations. Other weak vibrations are things like carbon-carbon single bonds. And then medium vibrations, those aren't super weak or super strong, are things like carbon-hydrogen and carbon-nitrogen single bond stretches.